Hey everybody, welcome to this lecture video on earthquake mechanics. So we're kind of switching gears now from the fundamentals of geology into geologic hazards and climate. So today we're going to be talking about earthquakes. So we're going to review different types of tectonic plate boundaries, and what is an earthquake. This is when a fault moves, basically it releases energy and shakes the ground. Talk about different kinds of earthquake waves, how something like the earthquake magnitude, which you might hear a lot about, what magnitude earthquake was that? How is that calculated? And we'll talk about earthquake frequency and this idea of earthquake forecasting. All right, so here is a map of where we have earthquake hazards around the world. You might notice, western half of the United States, parts of Alaska, all around kind of the western edge of North and South America. In fact, we have some geologic hazards, and along the India-Pakistan border up through Turkey, where they just had that really devastating earthquake that killed over 50,000 people. And the relationship between where we have earthquake hazards and plate boundaries is, for the most part, earthquake hazards are really only high if you live close to a plate boundary. And there are a few exceptions to that we will talk about. So for instance, if you look at, oops, sorry, not sure why it's zipping back and forth here. If we zoom into this earthquake hazard map of the United States, you can see obviously we have quite a lot of seismic hazards in California, where we have the San Andreas fault zone, where the Pacific plate borders with the North American plate. But then we also have this high seismic zone right on the corner of southern Missouri and western Kentucky and southern Illinois. And this is strange because usually we don't think about earthquakes happening far away from fault zones. And this is an interesting fault zone. It's called the Madrid Fault Zone. Geologists don't really understand why there's such a high earthquake hazard here. But we know that there is because there's been a history of earthquakes in that region. And where you find earthquakes once, you're likely to find them again. We're not sure when, but most likely there'll be a significant earthquake in that region in the future. So we're just going to talk about some notable earthquakes that you might have heard of. The last really big earthquake in California occurred in Northridge, which is a neighborhood of Los Angeles. It was a 6.7 magnitude earthquake. Well, the shaking only lasted 10 to 60 seconds, and luckily didn't kill too many people. Obviously, it was a tragedy. But compared to obviously hearing about the disaster in Turkey, you think, okay, we obviously maybe something was different about this earthquake, or this region was better prepared for it. But it did cause billions of dollars worth of damage. Highways collapsed. People were killed by collapsing overpasses and collapsing businesses and things like this. In Mexico City in 2017, there was a very large earthquake that killed around 370 people with magnitude 7.1. And it was really eerie. This earthquake actually happened on the same day of the year as the last really, really big earthquake in Mexico City, which occurred in 1985. And a lot of people, it was almost fortunate because a lot of schools and places like that were doing earthquake drills as a result of it being the anniversary of the big 1985 earthquake. That they were practicing earthquake safety and talking about what to do. And then, lo and behold, a a few hours later, the earthquake struck, so people had an idea of what to do. There was a really large earthquake in Haiti in 2010 that killed between 100 and 200,000 people. It was magnitude 7 earthquake. So you can see, magnitude 7 earthquake, in Haiti, killing, almost 200,000 people. A very similar magnitude earthquake in LA, a much more popular region, only killing 60 people. What is the differences here? Was this a natural disaster that killed this many people, or was it a human-caused disaster? Certainly that there's a lot of building code requirements that unless you don't enforce them, people are going to, build with materials that are not as strong. And this example in Haiti, I think one thing a lot of experts have realized is that a lot of the buildings were built with poor concrete, very, very weak concrete. Concrete is made of cement and sand and other particles, and the cement is what gives it strength. And there wasn't a very high percentage of cement in the concrete in a lot of the homes in Haiti. Obviously, it's a very underdeveloped country. There's not nearly as much funds for infrastructure. But what can the world do to help prevent disasters in areas where we know people are susceptible to natural disasters? How can we help enforce earthquake mitigation to prevent these kinds of tragedies from occurring? If a similar earthquake occurred in a region that had very strict building codes that were enforced with stronger materials and safer building practices, could we significantly reduce the casualty count from incidents like this? All right, so thinking about where plate boundaries occur and at what types of plate boundaries, we have the 3 different kinds of plate boundaries: divergent, convergent, and transform. And I think we already kind of did this activity in Google Earth. You kind of looked at what types of earthquakes occurred at different plate boundaries. At divergent plate boundaries, we mostly have shallow earthquakes that are not very strong. At convergent boundaries, where we have subduction zones, you can get really deep and really, really powerful earthquakes. And also at transform boundaries, where we have strike slip faults, you can also get really powerful earthquakes that are actually much closer to the surface and can be just as deadly as the type of earthquakes we get at convergent plate boundaries. And so this is what some of the plots that is possible to generate when you think about the types of earthquakes that occur at subduction zones. So this is a subducting plate going down here. And there's some very, very deep earthquakes that occur along subduction zones that can be very powerful. It's kind of a mystery because the earthquakes, we normally only think of earthquakes happening in the lithosphere where the rocks are strong, and the rocks down here are very, very, should be weak and in the asthenosphere and deforming ductily instead of brittly. So it's kind of a mystery how some of these deep earthquakes are occurring. So some things we talk about when we have an earthquake. What is actually happening when we have an earthquake is that we have a local fault and the fault slides. So the fault is stationary and then all of a sudden it slides. And the region that it starts sliding at along the fault plane, we call the hypocenter. This is the point within the Earth that is along the fault plane where the rupture is centered. And above the hypocenter, at the surface, we have the epicenter. And so the epicenter is just the location on the surface that's directly above the hypocenter. So the fault rupture area is the portion of the fault that actually slides. And sometimes the rupture area doesn't actually reach the surface. Sometimes it does. Sometimes you can actually see two sides that have moved. So this is an example of a rupture area. The fault ruptured right up to the surface right here. And this is a strike slip fault. So the where this guy was standing, that portion of the Earth's surface moved to the left and this portion moved to the right. But sometimes the rupture stays underground. All right, so like we said, we have a fault plane and then we have the rupture area. So what happens at the focus point, that's where the initial fault starts to move, and then the fault slip kind of projects outward along a fault slip plane. Kind of think about, maybe if your two hands are a fault, right? Maybe your palms are the first thing to slip, but then the rupture area propagates, and then maybe your fingers are the next things to slip, right? So initially it's just your palms, so that's the focus and where the rupture zone starts, and then boom, the rupture area propagates, and more of the fault starts splitting apart. So this is an example of a rupture surface in New Zealand that was really long. It was a 30-kilometer long rupture at the surface, and there was 2 meters of vertical displacement. So this is partly a thrust fault where the faults are coming together. So one thing that's kind of interesting is that really, really powerful earthquakes are fairly rare, but weaker earthquakes are more and more common. And the weaker the earthquake, the more of them that happen every year. So we'll talk about earthquake magnitude in a minute, but you guys probably already know that low numbers, like if you have a low earthquake magnitude, it's very weak. The shaking is not very intense. And the higher the magnitude earthquake, the bigger it is. So the most powerful earthquake ever recorded was in Chile in 1960. It was magnitude 9.5. I don't know why the slides are going freaking crazy. So those occur extremely rarely. There's been some pretty powerful earthquakes in Alaska and Japan that are close to magnitude 9. Those occur usually, less than one of those occurs a year. But we usually get a couple magnitude 8 earthquakes throughout the year on Earth. Somewhere on Earth, there's a magnitude earthquake once a year or so. And then there's maybe 20 or so magnitude 7 earthquakes that occur every year worldwide. And then, there's a few hundred magnitude 6, a few thousand magnitude 5 earthquakes occur every year. And then, hundreds of thousands of really small magnitude 3 earthquakes that you could hardly even feel. So the more powerful the earthquake, the more energy gets released. So for instance, a magnitude 6 earthquake releases as much energy as the atomic bomb that was dropped on Hiroshima in World War II. And if you think about the earthquake magnitude scale is logarithmic, so a magnitude 7 earthquake is 10 times as strong as a magnitude 6, right? And so, magnitude 7 earthquakes release, 10 times the amount of energy that atomic bombs do, right? So there are different kinds of earthquake waves. One kind of earthquake wave is called surface wave. These are seismic waves that travel along the surface only, and there's 2 different kinds. One's called a love wave, and one called a Rayleigh wave. And another kind of earthquake wave is called a pressure wave, where the surface gets compressed and compression waves kind of move through, and these can travel deep into the earth. And shear waves can also travel deep into the earth where it causes displacement up and down perpendicular to the direction that the wave is propagating. So each of these waves can cause damage at the surface, and because they can cause the surface to shake back and forth and accelerate back and forth. So for instance, an S wave moving through would move things up and down, and cause things like things to vibrate. Compressional waves moving through can cause damage, can cause cracking, and cause power lines to snap, can cause things that are extended horizontally to break if you kind of stretch and squeeze them, right? And love waves and Rayleigh waves, which kind of vibrate back and forth, can be some of the most intense and damaging. So what determines an earthquake magnitude? It's partly determined by a few things. Part of it is determined by how large is the portion of the fault that ruptured, so the area. The bigger the area of the surface that ruptures, the bigger the earthquake. How far does the fault slip when it suddenly slides? Because the fault is locked, and then during an earthquake, it suddenly slides by a certain amount. So the farther it slips, the more energy gets released and the more destructive the earthquake. And it also depends on how rigid the crust is. So we call this the shear modulus. So after we calculate the seismic moment, we can convert it to something called the moment magnitude, which is what we actually talk about when we talk about the magnitude of an earthquake. It's called the moment magnitude. So the moment magnitude measures the amount of energy released by the earthquake. It's logarithmic, right? So if you increase by 1, that's in magnitude, that's actually you're releasing 10 times more energy. And yeah, here's another plot of the amount of energy that get released by certain earthquakes. So this is the y-axis here is an equivalent tons of TNT that would explode. So the San Francisco earthquake of 1906, which caused basically most of the city of San Francisco to be destroyed, that's equivalent to the largest hydrogen bomb that was ever detonated. Some people use slightly modified intensity scales to discuss how powerful earthquakes are. You can use what's called a modified Mercalli scale, and that describes the intensity of the shaking that people actually feel. And so this is a shake map for the earthquake in 2010 in Haiti, and you can see that this is the what actually counts as how much shaking was there at the surface rather than what the fault was doing. So this got up to a magnitude 10 on this Mercalli scale. And so, like we said, the Mercalli scale is actually depends on how much damage occurred. It's kind of rated on how much damage occurs. So a magnitude 10 on the Mercalli scale would mean buildings and bridges are destroyed. Magnitude 5 would be you feel it, but and maybe small and stable structures are kind of displaced, like maybe a bookshelf falls over, but for the most part, there's not all that much damage. And then magnitude 12 is where things get really bad, and even well-built infrastructure can start to collapse. So like I said before, the frequency of an earthquake changes on depending how strong it is. We expect to have about 1 magnitude 8 every year worldwide, maybe close to 10 magnitude 7s. But this is kind of an inexact science. It's not like we're going to have exactly 10 magnitude 7s every year, or exactly 1 magnitude 8 earthquake every year worldwide. There's kind of just a probability that that's what it's going to average out to over the years. So one idea is that do earthquakes have a kind of recurrence interval? So this is an area of the San Andreas Fault called Parkfield, where there's been really regular earthquakes every 20 to 40 years, where we've gotten magnitude 6 earthquakes that occur on regular, like 20 to 30 year intervals. But now you can see, so that for a while, the San Andreas Fault was keeping up that pattern of creating these magnitude 6 earthquakes every 20 to 30 years. But then all of a sudden, after 1966, we haven't really had a big one. There was kind of almost a larger one in 2004, but it was a much larger period. And now it's been another close to 20 years since the last earthquake in that region. So can we expect another one soon? Faults don't behave like clocks, but there is a certain amount of stress that builds up over time. So kind of what's happening on a fault is far away from the fault. Like we said, we mostly get faults forming along plate boundaries. So one side of the plate boundary is constantly creeping along, and the other side of the plate boundary the other plate is moving in a different direction. So you're building up a kind of strain. So, we think the plate boundaries are constantly moving, so the strain is constantly building up. And then all of a sudden the strain gets released and the fault snaps and starts to slide. So this is kind of equivalent to, if you slowly bend a ruler, you're building up more and more strain, and then all of a sudden it snaps, and that's when the earthquake would occur, and the energy gets released. So that's maybe why we can expect earthquakes to kind of occur on semi-regular intervals, is that as the plates slide past each other at kind of constant speeds, maybe you eventually start sliding. So what kind of hazards do we get from earthquakes? Obviously, we get ground shaking. Ground shaking can destroy buildings. Like you said earlier, you really need to have buildings built up to code in order to withstand a certain amount of shaking that you can expect from an earthquake in that region. But if you don't have the funding as a country to do that, it makes you really susceptible to serious disasters when those earthquakes do occur. Earthquakes also cause tsunamis, right? So this is an actual picture of a horrifying tsunami that occurred in Japan. So tsunamis don't really look like this, right? Where they're just like a giant wave. They look more like this, where kind of the sea just kind of rises up and gets pushed higher and higher. The sea level gets higher and higher and pushes further and further inland. So here's another picture of a devastating tsunami that occurred in Japan that was triggered by an underwater earthquake. So what type of earthquakes typically create tsunamis? The rupture zone has to be underwater, and the rupture has to cause vertical motion. And it's the elastic, we call it the elastic rebound of the overlying plate, kind of pushes up and pushes the ocean up. And when the ocean gets pushed up, it causes a wave at the surface of the ocean, which then projects onto the land. Tsunamis are most likely to get generated at subduction zones, where we get large magnitude 8 earthquakes that can be generated. So I wanted to explain this idea of elastic rebound. So when when the oceanic plate is subducting underneath the continental plate, it kind of starts dragging the overriding plate down with it. So the overriding plate slowly over, thousands of years kind of gets flexed downwards. And then when an earthquake occurs, suddenly, instead of the two surfaces being stuck together, the continental plate or the overriding plate slides up back to where it wants to be, and it pushes the ocean upwards, and the wave gets generated at the surface and moves inland. One thing that also happens, let's say you had a house right here before the earthquake occurred, and then the earthquake occurs, and all of a sudden, even after the tsunami passes, you would now be underwater because the surface was kind of flexed upwards, and then it kind of snaps down after the earthquake occurs. And so overall sea level can rise relative to the land after a megathrust earthquake like this. So one of the deadliest natural disasters ever occurred in 2004 on December 26th. There was a magnitude 9.3 earthquake off a subduction zone off the coast of Sumatra. And it created a tsunami that killed over 200,000 people throughout throughout Indonesia and the Philippines, and it killed 20,000 people in India and Sri Lanka, and there was even casualties off the coast of Africa. So there was this sped a giant tsunami all throughout these very low-lying island nations. And it's very sad. It killed a lot of people. So what can we do about this in the future? Well, obviously we want to have warning systems to warn people because often the earthquake gets detected before the tsunami reaches land, and so sometimes you can have 20 minutes of warning or even an hour of warning before a tsunami arrives. And so with proper warning systems and public education, can we prevent casualties from being this high in the future from similar events? So when these waves come ashore, sometimes they break up into multiple waves, and this is kind of what happened with the tsunami. And tsunamis can also travel really, really far. This is an example of the tsunami that got generated from the largest earthquake ever measured in Chile, off the coast of Chile. It created massive tsunamis that traveled all throughout the Pacific Ocean. And there was even a tsunami in Japan that the tsunami reached Japan about 24 hours later, and caused some damage there. Interestingly enough, in the northern United States, we've never had a tsunami in Western recorded history. But in the year 1700, we think that there was a large magnitude 8 earthquake that occurred off the coast of Oregon in this region called Cascadia, because around that time there was a large tsunami detected in Japan and recorded in Japan. And indigenous peoples of the Pacific Northwest also described a devastating tsunami. And we also have what's called paleoseismic records. Sometimes you can look at sediments in the rocks to understand if an earthquake occurred in the past. The earthquake can kind of get recorded in the sediments and in the rocks. So then paleoseismology study of ancient earthquakes, reveals that probably every 300 years or so, it seems that this region has large magnitude 8 earthquakes. So here we are around over 300 years later since the last magnitude 8 earthquake. Are we due for another one again? It's difficult to tell when it will happen, but the paleoseismology studies that suggest that this fault slips on average every 300 years suggests that, the probability that in the next 50 years we have one are fairly high. And so what could we expect from a tsunami? Well, there is kind of other interesting remnants of this 1700 tsunami that are visible on the coast of Oregon still. For instance, there's an area on the beach where there's all these tree trunks in the sand. And we haven't had sea level go up all that much in over the 300 years. So what happened here? Well, what happened here is that the land used to be higher, but then when that earthquake occurred, the land probably subsided by 5 to 10 meters. And this area that was well above sea level is suddenly now below sea level, and all those trees got destroyed. All right, another type of hazard that earthquakes can cause is this phenomenon called liquefaction, where the shaking of the ground causes soils that are saturated with groundwater to suddenly liquefy and lose all strength. So if you build a house on, loosely compacted sedimentary rock that has lots of groundwater in it, and then all of a sudden an earthquake comes through, the rock you're sitting on is basically going to turn into a pile of mush, right? The shaking kind of causes the sand grains that are suddenly touching to suddenly just be floating, and the material loses all strength, so it can really cause significant damage. So this is an example of liquefaction that occurred in an area off the coast of Alaska. And you can see that the ground kind of subsided quite a bit because the ground kind of lost all strength and turned into mush. And here is an example of liquefaction that occurred in a region in Japan during an earthquake. So this would be, these buildings were all built on sedimentary rock that had a lot of groundwater in it. And when the liquefaction occurred, the ground just turned to mush and the buildings just tipped over as if they were built on, slush. So liquefaction can do quite a lot of damage. This is liquefaction in Palu in South America, before and after satellite image, where dozens of buildings were just completely destroyed because the ground they were on just completely turned to mush and could no longer support anything. Obviously, land movement can occur and slide around, and gaps can open up. And this doesn't cause most of the damage. Mostly it's from shaking and liquefaction and sometimes tsunamis. And the other thing that can happen when this is more of a human-made disaster, but fires can also be generated by earthquakes. If gas lines rupture or electrical lines break, right, it can cause massive fires. And so this is an image of San Francisco in 1906. The earthquake caused a really significant amount of damage in 1906 in San Francisco, but the main thing that really wiped out the city was the fires that raged on for days. So massive fires broke out, firefighters were completely overwhelmed, and neighborhoods just completely burned. And there's actually some, very troubling accounts of kind of racism playing a factor in letting these fires burn out. Firefighters focused on putting out fires in wealthy white neighborhoods, and they may have even intentionally let the fires burn on longer in parts of the area where you had a lot of Chinese citizens. There was a lot of racism towards Chinese people in the area, and so a lot of Chinatown got burned down for days and days, and firefighters kind of refused to put it out. So very sad, but thought it was important to mention. Earthquakes can also cause landslides. When the ground starts shaking, mountains that are semi-stable, might have slipped one day anyways, can suddenly slip. And so landslides often accompany earthquakes. So people are thinking a lot about, ways to retrofit infrastructure so that they're built stronger. There are a lot of different techniques. I'm not really going to go into them. But one thing that you see a lot of in California is these like cross-cutting steel beams that can really support motion and support the strength of a building in a large earthquake. And another thing people are doing these days is at the base of large apartment buildings, they actually put kind of like shock absorbers below, so that when the ground shakes, it doesn't shake the building, and the building can stay closer to still while the ground below moves back and forth, and the motion is kind of absorbed by these like flexible shock pads. So a lot of building requirements in California require these types of precautions to be taken when building new construction. And there's billions of dollars going into retrofitting, rebuilding bridges that are older so that they are safer and can maybe sustain larger earthquakes in the future. All right, I hope you liked the video, and looking forward to people's talks that they'll be giving the week after I return.